So we talked about the Lyapunov approach to stability, and the main theorem was for a given, let's say, autonomous system, for simplicity, for a given autonomous system whose for which origin is an equilibrium point. The asymptotic stability of that equilibrium point can be established by the existence of function, which we call the Lyapunov function, provided that it satisfies certain conditions, like the positive definiteness and the negative positive definiteness of itself, and also negative definiteness of its time derivative. Now, there's an interesting question. Okay, so it's interesting from the application, certain applications point of view, and also it's interesting on its own right, which is that if we have, for a system for which origin is an equilibrium point, if the origin is asymptotically stable, then can we establish that asymptotic stability by a Lyapunov function? Okay, so once again, we know that if we have a Lyapunov function satisfying certain conditions, we have stability. And now we're reversing the order of things and start from stability and try to reach, if it's possible, to the existence of a Lyapunov function. Okay, so namely, this is what we have seen. Okay, or we know that existence of a Lyapunov function implies stability. Okay, Lyapunov function satisfying certain conditions. And now we ask whether the reverse implication is also valid. Okay, so stability does imply stability or stability existence of a Lyapunov function. Okay. Now the answer turns out to be affirmative. Okay, the answer is positive, and such question under different conditions have been studied under the title converse Lyapunov theorems. Okay, there are many versions of it. Okay, and I'm going to give one of the most general ones soon enough to reference for those of you who are interested. So, and the analysis is a little bit sophisticated. Okay, there are many subtleties that one has to be careful about, but the main idea is quite simple. Okay, the main idea in obtaining a Lyapunov function from a given system whose origin is asymptotically stable. Okay, so we will try to now understand or get a glimpse of that main idea, general idea, and then we will and we'll talk about it, and then we will state the theorem, the converse Lyapunov theorem that's in our text, and then we'll move on to other examples. Okay. So to understand this direction, that this direction holds, or how a Lyapunov function is constructed from a system with some asymptotic stability properties of its origin, we're going to consider the linear case, because things are easy to deal with and see notation-wise for a linear system. Okay, so let's study the linear case. Okay, and by studying linear case, we're going to be doing the following. Given a linear autonomous system, LTI, x equals a of x, okay, and for which suppose that the origin is known to be asymptotically stable, which is equivalent to that all the eigenvalues of A matrix, the system matrix, are with statistically negative real parts. Okay, starting with that x dot equals a of x, we will try to obtain a function, a Lyapunov function, which satisfies the conditions of the Lyapunov stability theory. Okay. So, this is the system we start with. X dot equals A of X. Okay, an n-dimensional system, therefore A is a constant n by n matrix. And suppose that the origin is asymptotically stable. Okay. Then, to construct the Lyapunov function, what people do is, especially for non-linear systems, they take the solution. Okay. Phi x of t. Now we're introducing a new notation, and this notation is sort of necessary for the future analysis that follow, and but it's a very simple notation. Now, until now, we wrote down solutions as x of t, but now we want to be careful about the initial state. We want to call it x, not x of t0 or x of 0, and for that we use this notation. Okay, phi x of t equals e to the a t times x. Okay. So x is the initial condition, that is the value of the solution at t equals 0. We take t equals 0 without loss of generality, our initial time. Okay. And for a linear system, we know the solution. It's simply state transition matrix times the initial condition, okay, for any given future time t. Okay. So here we treat x as a constant, okay, a constant vector, our initial condition is our initial condition, meaning that the solution at time t equals 0 equals x, our initial state. Okay, now asymptotic stability is equivalent to exponential stability for linear time varying systems. And since the origin for our LTI system is asymptotically stable, that means we can find constants k and lambda such that the norm of the solution is always upper bounded by k e to the minus lambda t times the norm of the initial state. And the norm of the initial state is norm of x. Okay, we can always find k and lambda, and that's satisfied. Now, we will introduce or define or construct the Lyapunov function from the solution, the very solution itself. And the trick is the following. Define v of x as follows. Okay. V of x equals 0 to infinity phi x of t square dt. Okay. Now this, here we have a norm. Okay, norm is a scalar function, and we're taking its square. It's still a scalar function, and also it's always non-negative. And also, since the norm of the solution is exponentially decaying, or upper bounded by some exponentially decaying function, its square is also exponentially decaying. Therefore, this integral, even though the length of integration is infinity, is well defined. It always gives us some number. Okay, and that number will depend on the the initial state. Okay, if the initial state is close to the origin, it will be this integral will be small. If it's large, it will be large, and so on. Now, this is well defined due to the fact that the norm of the solution is exponentially decreasing. And this we can write as from 0 to infinity, solution transpose times solution. So we're taking inner product of solution by itself. So that's the very definition of norm square. And what's the solution? Solution is, in terms of the initial state and state transition matrix, is e to the at times x. Therefore, norm square of the solution is this guy transpose times itself, e to the at x. Therefore, we have solution transpose, which is x transpose e to the at transpose, which is e to the a transpose t. It's the same thing. Times solution, which is e to the at times x. Now we're integrating that. Note that here x is a constant. It's not x of t. Okay, we're using a different notation. Since x is constant, we can take it outside integration and write this as x transpose x, and in the middle we have this e to the a transpose t, e to the a t dt. Now this thing is scalar, whereas this thing is also scalar, but this is a vector transpose, therefore it's a row vector, this is a column vector, and in between what we have is this. Now what we're integrating is e to the at, it's an n by n matrix, time varying, and likewise e to the a transpose t is its transpose. Therefore, here we have two matrices multiplying themselves, and those are both square matrices of the same size. Therefore, here we have an n by n matrix, and clearly its integral will also be an n by n matrix. Okay? So what we are having here is x transpose times some n by n matrix times x. Therefore, this v of x is a quadratic function of x, which is our initial condition. Note that v is quadratic and it's positive definite. Okay. Why it's positive definite? It's positive. Well, it's a quadratic function, that is x transpose times some symmetric matrix times x. Therefore, v being positive definite is equivalent to this matrix, this symmetric matrix in between being positive definite matrix. Okay, and this is a positive definite matrix. Why? Because e to the at, here this is some matrix m, and here this is transpose n transpose n. So any matrix of this form is always positive semi-definite. Okay, but now this n is not any n; it's e to the at. And e to the at state transition matrix, if you remember from 542, it's always a non-singular matrix. Therefore, this is always a non-singular positive definite, non-singular positive semi-definite matrix, and non-singular positive semi-definite matrix is a positive definite matrix. All the eigenvalues are strictly positive. Okay, therefore, at each time, this thing is a positive definite matrix, and then you're integrating this positive definite matrix function, and the result is also a positive definite matrix. Therefore, this v of x is quadratic, and it's a positive definite function. Now, we have established the positive definiteness of v, our Lyapunov function candidate. Okay? In order for that v to establish asymptotic stability of the origin, we also require its time derivative to be negative definite. And now let's see that is the case, okay, with this special construction of a Lyapunov function. So we have established the positive definiteness of v. Now the next step is negative definiteness of its time derivative. How about v dot, or its definiteness properties? Now let's compute v dot of x as follows. V dot of x is, now when we put dot here, we're talking about the function v of x of t. Now x of t becomes the solution, okay? The notation, I admit, is a little bit confusing here, but it's not that confusing, I think. So v dot of x, therefore, is along the solutions of the system is what? Now this is v of x. This integral is a constant matrix. So we're talking about x of t transpose, let's call it p, some positive definite matrix, constant, times x of t. Okay, so this is our v of x of t. And this thing here is p, our positive definite, symmetric positive definite matrix. And now we're trying to evaluate v dot. Okay, now v dot is, for such v, quadratic v, is x dot transpose times p, which is dt x plus x transpose dt x dot. Okay, and what's x dot? X dot is a times x. So this is therefore x transpose times a transpose, and this x dot here is a times x. Okay, that's coming directly from the system equation. Now, in therefore replacing x dot with a times x, we have what? X transpose times a, and here we have a times x. And since a is a constant matrix, we can put it inside integration without affecting anything. And once you do that, and then combine both integrals, because they both for the same interval from 0 to infinity, we can write the whole thing as from 0 to infinity a transpose e to the a transpose t plus e to the, plus e to the a transpose t e to the a t times a, and then we have dt times x. Okay. From this step to that step, we use nothing other than the system equation x that equals ax. Okay. Now there's one nice thing about this integrand, and it is d of a transpose t e to the a t. Okay. Or in other words, e to the a transpose t times e to the a t, that square time-nary matrix's time derivative is this term here, the integral. Okay. And the reason for that is d over dt e to the at. Okay, if you remember from 542, this equals a times e to the at, or e to the at times a. Those two matrices, they commute. Because of that, this equals that. Okay. Hence, we can write x transpose. Now, this thing here is d of something. Therefore, clearly, when you take the integral, what you obtain is this thing, whose derivative appears as the integral. Hence, we have x transpose times e to the a transpose t e to the at, evaluated from t equals 0 to t equals infinity. Okay, this matrix times x. And this equals what? Now everything will simplify to a very nice expression. Again, remember the properties of e to the at. It's, first of all, e to the at, since x of t is converging to 0 as time goes to infinity, because the system is asymptotically stable, x of t converges to the origin. It converges exponentially. Since x of t was e to the at times initial condition x of 0, that means e to the at converging to the 0 matrix exponentially. Okay, so at t equals infinity, if you evaluate that, these two matrices must be 0. Okay. And at t equals 0, again the property of state transition matrix, t equals 0 is identity matrix. Okay. Therefore, this integral gives us 0 matrix minus identity matrix, which is minus identity matrix. And then what there is x transpose times minus identity matrix times x, which is no other than minus x transpose x, or minus norm of x squared. And that's a very nice right hand side, because on the left we have v. So we have positive definiteness of v, we have negative definiteness of its derivative. Therefore, that's a perfectly valid Lyapunov function through which we can establish its stability. Hence, v dot is negative definite. Okay, so what we did here is, from a system whose origin is known to be asymptotically stable, we constructed a Lyapunov function by simply integrating some function of norm of the solution. In this case, it's the square of the norm of the solution. And that gave us a function which is positive definite and whose time derivative is negative definite. Okay, so what we have established here is, for a linear system, we have established that if the origin is asymptotically stable, then you can always find a Lyapunov function, in fact, not any Lyapunov function, but a quadratic Lyapunov function, through which you can establish that stability. And let's write that conclusion down, because it's important on its own line, and also it's important from the point of view that it served as a starting point for the nonlinear generalizations, which was quite a lively research topic until recently. Conclusion. V of x constructed as 5x of t squared dt works as a Lyapunov function. Okay. And this, or similar ideas, have been used to move to the general nonlinear case. Lie behind the converse Lyapunov theorems. See, for instance, this is one of the most general results out there about converse Lyapunov theorems. It's a smooth Lyapunov function from class KL. Yes, then so note that this class KL is class of functions that we talked about, one of our comparison functions. It's by and Thiel and Lauren Prolly. Okay, this is 2000 paper. Okay, and later on, this result has been extended to the discrete time case by some authors, among which the most significant one is Christopher Kelly. Okay, those are the words. Now, let's state the converse theorem, which we will not prove, but as I said, it's, the proof technique is quite similar to what we did with the linear system. Of course, you have to be careful about many details when you're dealing with the non-linear case, general case. This is the converse Lyapunov theorem from the text 417. Let the origin be global asymptotic stable equilibrium of some autonomous system. Okay. F of x, where f is locally Lipschitz. Very mild assumptions. Then it turns out you can always find the Lyapunov function. B Rn R together with comparison functions alpha 1, alpha 2, and alpha 3 class K function, such that you have the following conditions satisfied. Okay, v of x is sandwiched between the norm of x passed through class K field functions alpha 1 and alpha 2, and v dot, or the product gradient of v with f of x is upper bounded by the norm of x passed through minus alpha 3 for all state x and r. Okay. Now let's talk about an example in the last part of our lecture. It's an example from the text. Example 445. Now, we will try to determine the stability properties of the origin for the following system. x1 dot equals some function h of t, perhaps representing some unmodeled effects, unmodeled parameters in the system. And we have another function g of t, x1 cubed. And x2 dot is minus h of t, x1 minus g of t, x2 cubed. Okay, so it's a non-autonomous system. We have certain conditions that are satisfied by the functions h and g, and they are as follows. They're bounded. Okay, that is, you can always find two numbers, and norm or the absolute value of that function is always between those two fixed numbers. They're bounded and differentiable. Moreover, g of t is never less than some positive constant k. Okay. For all times. Okay. Now for this system, you ask the following questions: is the origin uniformly asymptotically stable? B. Is the origin exponentially stable? And here we will use theorem 450, which we didn't talk about in our lectures, but let me write it down here. The origin of x that equals f of tx, the origin of the non-autonomous system, is exponentially stable if and only if the linearization x that equals a t of x with a of t defined as the following Jacobian partial x f of tx. Okay, evaluated at the equilibrium point, the origin is exponentially stable. Okay. So the exponential stability of the origin can be checked in an if and only if fashion by its linearization. Okay. Note that we cannot use linearization to check asymptotic stability. I mean, not always. Okay, so that's B, and C and D is as follows. C is x0, origin globally uniformly asymptotically stable. And finally, D is the origin globally exponentially stable. Okay. So we will try to characterize the stability properties of the origin in quite a complete way. Here is one way to approach to attack the problem. Let's consider A and C together. Okay. In A, we're dealing with uniform asymptotic stability, and in C, global uniform asymptotic stability. If somehow we can show directly that the origin is globally uniform asymptotically stable, that is, if we can answer C yes, then we don't have to worry about A because automatically A is satisfied. Okay. So let's work with the following Lyapunov function, which is usually the first choice norm square. Okay, for any system. Usually it doesn't work, but sometimes it does. So v of x is 1/2 x1 squared plus 1/2 x2 squared. Okay. We introduce 1/2 so that when we differentiate, we don't have to deal with those twos. So in reverse, we have the norm of x squared over 2. This is our Lyapunov function candidate. Now we will try to establish asymptotic stability of the origin through that. Okay. For that, well, it's clearly positive definite and radially unbounded. Therefore, what we have to show is, if you want to show asymptotic stability through that Lyapunov function, we need to show that its time derivative is negative definite. Okay. That V yields the following: V dot equals x1 dot plus x2 dot. Okay. Okay, so and that V dot can be written as x1 times. What's x1 dot? X1 dot is here, it's given right hand side. H of t x2 minus g of t x1 cube plus x2 times minus h of t x1 minus g of t x2 cube. Okay, now we have a nice cancellation here. Here we have x1 h x2. Here we have x2 minus h x1. Therefore, this and that, they cancel out. And what we're left with is minus g of t times x2 to the 4. Okay. Now, that's clearly what this thing is, a negative definite expression, x1 to the 4 plus x2 to the 4, but that's multiplied by some time-varying function. And in order to be able to claim something in a uniform fashion, what we require is we want to express the upper bound on beta independent of time. Okay? And that we can do because, for this case at least, because g of t can be lower bounded by something fixed, something that's time invariant. So that's less than or equal to what? Now g of t is greater than k, so that means minus g of t is less than minus k. Therefore we can replace this minus g with minus k. Minus k. Now this is a constant. Okay. x1 to the 4 plus x2 to the 4. It's more or less now obvious. We have uniform asymptotic stability, but to be able to apply theorem 4.9 directly, let's express this thing in terms of the norm, a function of the norm. Okay, and we're using Euclidean norm. Now, this, it turns out, is less than or equal to something, okay, minus k over 2 times norm raised to the power 4. Okay. And from this step to this step, we use a few lines of tricks. Let me put them down here. Okay, here is the reasoning in this step, which we denote by star. So x1 square plus x2 square. Okay, so this is x1 to the 4 and x2 to the 4. x1 to the 4 plus x2 to the 4. This we can write as 1/2 x1 square plus x2 square. Okay. 1/2 norm square. Okay, now if you square the norm, what you have is x1 to the square the norm square, what you have x1 to the 4, x2 to the 4, and also we have some cross terms, which is 2 times x1 square plus x2 square. To get rid of that, we have to subtract this x1 square plus x2 square. And also, what we have is 1/2 x1 square plus 1/2 x2 square. Okay. Now, if you add all these terms, what you obtain is x1 to the 4 plus x2 to the 4. Now, why did we write this x1 to the 4 plus x2 to the 4 in this long, complicated fashion? The reason is as follows. This equals, okay, this is 1/2, and then this is norm square, and then we're squaring once again. So what we have is norm raised to the power 4. And that thing is what? That thing is plus 1/2 x1 square. Okay. Minus 2 2x1 squared x2 squared plus x1 to the 4. And this is x2 to the 4. Okay. This thing is x1 squared minus x2 squared. Okay. So clearly this is never negative. Therefore, this thing can be lower bounded by 1/2 norm of x to 4. Okay, by getting rid of that term. So x1 to the 4 plus x2 to the 4 is always greater than or equal to 1/2 norm of x raised to the power of 4. Therefore, minus that thing always less than or equal to minus 1/2 norm of x raised to the power of 4. And that's what we did here. This guy is minus x1 to the 4, x2 to the 4 is always less than or equal to minus norm of x raised to the power of 4. Okay. So, what we have is, therefore, alpha 1 of x less than or equal to mu of x, alpha 2 of x. Okay, so this is the condition, the first condition in our Lyapunov theorem. And b dot of x less than or equal to minus alpha 3 over of norm of x. Now, the question is, what are alphas here? Alpha 1 and alpha 2, they're directly s over 2. Okay, they're just linear functions with s squared over 2, excuse me, with alpha 1 of s, alpha 2 of s equals s squared over 2. Okay. Because here we have g of x equals norm of x square over 2, therefore it's less than equal to and also greater than equal to the same thing. Okay, norm of x squared. Norm of x squared is norm of x passed through the function s squared over 2. And alpha 3 of s equals k over 2, s to the 4, and k is a positive number. Therefore, alpha 1, alpha 2, alpha 3, they are all class k infinity functions. Okay. Then, by theorem 4.9, we have global uniform acidic stability because those inequalities hold throughout the entire space. And once we have global uniform acidic stability of the origin, we have uniform acidic stability of the origin automatically. Okay. Therefore, the origin is globally uniform acidic stable and also uniform acidic stable, obviously. Now let's move on to the remaining parts, parts B and D. For that, we are advised to use the linearization method. Now, A of t, Jacobian of f, evaluated at equilibrium point is 0, h of t minus h of t, 0. Okay, it has this form. Now, is the linear time varying system. Okay, now we will study stability, exponential stability properties of the origin through the linearized system. Eta dot equals AT times eta. Let eta denote the state of the linear system. Is this system exponentially stable? Okay, so that's the question. Note that for an LTI system, to determine exponential stability or asymptotic stability, because they're the same thing, all we have to do is look at the eigenvalue locations for a constant A. When A is time varying, you cannot do that. Okay? For time varying A, or for time varying linear system, eigenvalue locations doesn't tell you anything about the about the stability properties of the origin. Even the eigenvalues are fixed, okay? If they are constant, okay? A time varying A matrix may have constant eigenvalues. Even in that case, eigenvalue locations doesn't tell you anything about the stability in general. Okay? So let me put that important remark down. Note that the eigenvalues of time varying system matrix tell in general nothing for the stability properties of x that equals a t x. There's a very nice example in the text. Example 4.22. Okay, so you may go and check that. Now, what we have is now the linear system. A to that equals a of t times a, and a of t we obtain in here. Okay. Since we cannot use the eigenvalues, what we can use is the only thing that we can use, which is the open function approach. Okay, so let's try our chances with the first choice for the open function. It's norm square, or 1/2 norm square. 1/2 eta 1 square plus 1/2 eta 2 square. Let's see, clearly this is a positive definite function. Let's see what can be said about its time derivative. Okay, so v dot is at eta. Okay, so that's the time derivative in product of the gradient with the right hand side. Okay. The transpose of the gradient is eta 1, eta 2, and the right hand side is A matrix times eta 1, eta 2. And A matrix is 0, ht minus ht0. Note that we don't have to worry about h of t to compute this product, because A of t is a skew symmetric matrix. That is, its symmetric equals its negated version. And whenever we have a skew symmetric matrix, x transpose times that matrix times x is always 0. In this case, we have v dot equals 0. Okay. V dot equals 0 tells us everything that we need to know about the exponential stability properties, if such properties exist, of the origin. Okay. So V dot equals 0 means solutions pass through the Lyapunov function, which is here, norm squared over 2, is constant. Excuse me. Not 0, but it is constant. So it equals the initial value, whatever it is. So since it's constant, clearly it's not converging to 0. It's not converging to anywhere, as a matter of fact. It has already converged to the constant value. So since this guy, the Lyapunov function, is not converging to the origin, and the Lyapunov function is a positive function, that means the state itself is not converging to the origin. Therefore, the origin of the linearized system is not asymptotically stable, because we don't have convergence. Then eta equals 0 clearly is not exponentially stable, because this is even a stronger version of convergence or stability. And then the origin of the nonlinear system, the original system, is not exponentially stable. And for this step, we use theorem 4.15. And if the origin is not exponentially stable, clearly it's not globally exponentially stable either. X equals 0 is not globally exponentially stable. Okay, that completes our second part of the solution, B and D.